Stanford University.
Okay, I think I will start. It's exactly 4:15 according to my watch, which was set by Naval Observatory time this morning. So it's a real pleasure for me to introduce Rod Ewing, who's sitting over here. I first got to know Rod in 1973 when I arrived at Stanford. In fact, I guess I met you the year before that, or even the year before that. I came out twice to interview and was finally convinced the second time to accept. Rod was a graduate student here, but he had sort of a checkered history before that. He did his undergraduate work at Texas Christian, which was erroneously ranked above Stanford in the football polls at the end of the season, but we'll forgive him for that because he's also a Stanford graduate. He came to Stanford in, I think, 1968, and he tells me, in fact, I knew this at the time, I just forgot the dates, but he was immediately drafted into the Army to fight in Vietnam. And so he started his graduate career, but then he was whisked off to the Far East, the southeastern Asian part of the country or the world, and he actually took part in what I consider probably the biggest oxymoron of all times, which is military intelligence. So he was in military intelligence. That means he was sort of a spy, and he was in Cambodia for part of that time, and I guess he came back directly from Cambodia to Oakland in his jungle fatigues, and then came to Stanford after he changed clothes and sort of re-enrolled here and finished up his PhD. So I was fortunate to be on his committee, as was Louis, the last years or so of his career here, and he has gone on to become a very distinguished graduate of Stanford and a great scientist. In fact, when I first found out what he was doing, working on niobium tantalum oxides, I said, why are you doing that? Because there are many more important things to look at, such as order, disorder, and feldspars, that you should be, And Rod actually made the right choice because he knew there was going to be a nuclear waste problem later on, and he also knew that these strange niobium tantalum oxides and other things like those were going to be wonderful places to store some of the elements that we consider the highest level nuclear waste. So he really did make a good choice. He went to the University of New Mexico after that. He became a Regents professor there, and he then retired and was attracted away by the University of Michigan in Ann Arbor. He's actually the Krauss Distinguished University Professor of Geological and Sciences at Ann Arbor, University of Michigan. He's also Professor of Nuclear and Radiological Sciences and also a Professor of Material Science and Engineering. So he's actually impacted all of those fields in a rather significant way. He's won a number of awards. In fact, I just brought this because it's the most recent award he's won. This is just hot off the press, and it's the fact that he's been elected as a Foreign Associate of the Royal Society of Canada. And I'd like to read to you the citation here just to set the stage for Rod's talk. Rodney C. Ewing is recognized as the world's leading scientist on the geochemistry of uranium and the role of uranium in all aspects of nuclear power, from nuclear reactor processes to safe storage of radiogenic waste. With his intellectual capabilities and scientific expertise, he's made major and fundamental scientific advances in earth and environmental sciences. He has tirelessly pursued geological solutions to the problems of nuclear waste disposal, almost single-handedly impressing on the materials science community and government agencies that the importance of this approach. This work represents the most creative and sustained scientific initiative in this field since its inception. So that was a citation for his induction into the Royal Society of Canada. I am also pleased to tell you that Rod's won a number of awards. Other than this, he's an honorary professor from the University of Paris 6. I guess a couple of years ago he got that nice recognition. So he has many, many ties to international scientific collaborators and has done a very effective job as an international sort of spokesperson for our community in this country with the rest of the world. So without further ado, it's my pleasure to introduce Rod Ewing.
So, of course, thank you, Gordon. I'm flattered the citation is a little bit of an exaggeration. This is a wonderful homecoming for me. I first stepped into this room in 1968, and as I look at the audience, I realize most of you weren't born then, so this is also a little bit discouraging. The title is clear. I want to talk about plutonium, and both from the nuclear perspective and from the geologic perspective. I want to immediately acknowledge the help I've had from postdocs and graduate students and undergraduates over the years. This is a photo of the group as it existed about a year ago. More people have been added since. But it's been through the students, particularly through the graduate students and postdocs, that we've been able to do a lot of this work. And very specifically, I want to thank the Office of Science, Basic Energy Sciences, for funding our work over several decades, because actually no one was interested in this. And in fact, they are specifically not interested in waste management or waste disposal. Their admonition to me always was, that could be your hobby, but please don't say anything about it in your papers, because you have to stick close to the science. Now, of course, they're quite happy that the work has an application when they go to Congress for their funding. All right, to put everyone on the same page, I want to discuss a little bit what goes on in a reactor when you put uranium into the reactor. The fissile isotope of uranium is uranium-235, and as geologists know, this is very rare. Less than 1% of the uranium in the ground is 235, but it's unstable enough that when it's hit by a thermal or a slow neutron, it fissions, and so you get the fragments of the nucleus. You get some extra neutrons, which now have a lot of energy. They have to be slowed down. But this is the beginning of the chain reaction. And then you get a considerable amount of energy, about 200 MeV. Okay? The fission fragments, as I said, this is just a splitting of the atom, so you end up with this bimodal distribution of new elements like cesium and strontium, technetium and iodine. The means on this bimodal distribution are approximately 90 and 140. And these elements are the elements that we most often worry about in terms of nuclear waste disposal. So strontium-90, cesium-137, cesium-135, technetium-99. Well, that's the energy-producing part of what's going on in a reactor. But at the same time, the uranium-238, which is more stable, it captures neutrons. And through a series of neutron capture, gamma ray emissions, and then beta decays, finally you create the plutonium-239, okay? As well as minor actinides. And the minor actinides, I've just clipped out a piece of the periodic chart, are neptunium, americium, and curium. The plutonium-239 is really at the heart of the matter. And you get other isotopes of plutonium. I'll show those to you in a moment. But the plutonium-239, what to do with it really drives a lot of the concepts of advanced fuel cycles, geologic disposal, and so on. My nuclear engineering colleagues want to take this plutonium-239, get it back into a reactor because it's fissile. It can be split with thermal neutrons and make more energy. Okay? So that's the nuclear engineers. People worried about weapons proliferation are not so excited at the possibility of separating the plutonium-239 from fuel, because once separated, it could be diverted and used as a fissile material in a nuclear weapon. And of course, from a disposal point of view, or as a geologist, we're very concerned about what happens to transuranium elements, particularly plutonium isotopes, when they're released to the environment. If we put spent fuel in the ground, what happens to the radionuclides from the fission event, but also I'll show you that the fate of the transuranium elements is quite important. Okay? Now, it's not only plutonium-239 that's created. This is a little more elaborate picture of the series of nuclear reactions that takes place. You get this line of plutonium isotopes. Approximately 60% of the plutonium is the plutonium-239. And what's very important to realize is this mixture of isotopes, plutonium isotopes, in the used or spent nuclear fuel, once separated, is entirely weapons usable. Okay? It's not wonderful weapons material. There are problems with it, but it is weapons usable. So that's part of the very serious concern about the fate of these transuranium elements. Now, imagine since 1941, when plutonium was first created in microgram quantities, we now, through nuclear reactions, have over 2,000 metric tons of plutonium. 2,000 metric tons of anything for a geologist doesn't sound like much, but in terms of its critical mass, we have to keep track of quantities that are less than 10 kilograms. So 10 kilograms out of 2,000 metric tons is not much. Also, if you look at the distribution of the global inventory of plutonium, you'll see about 250 metric tons are in weapons. And it turns out that's good because people have a tendency to keep track of their weapons. They're numbered, and you have a log that tells you where you left them. But an equal amount, 250 metric tons, is plutonium that's been separated from what's called civil spent fuel. This is fuel that was used to generate electricity. It was separated with the hope of putting it back into a reactor, the plutonium, and I'll discuss the various forms. But the fuel cycle is out of balance, so we've accumulated 250 metric tons of separated plutonium scattered around the world, and in some cases looked after very carefully, and as you might imagine, in other cases looked after less carefully. Okay? So what I'd like you to, maybe the take-home message early is, if you think of global inventories, we have on the upper right the iconic diagram for CO2, and I'd suggest that on the upper left, we should also be keeping track of the plutonium. Okay? And that inventory grows over time. And in fact, these inventories are related, because if you think about the discussion of solving the CO2 emissions problem with nuclear power, the question is, what type of fuel cycle, how many nuclear reactors do you need to have an impact on the carbon cycle? And then given the scale and the different types of fuel cycles, what are the weapons proliferation issues and what are the waste disposal issues? Because we have geochemical cycles for all of these radionuclides. So those two upward turning curves for plutonium and carbon are related. You can't, in the discussion of nuclear power versus fossil fuels, you have to think about what products you're generating. Now, in the broadest sense, there are two strategies for handling this plutonium. The nuclear strategy involves getting it back into reactors to burn down that inventory and take advantage of the energy content of that plutonium. You get it back into the reactor by mixing it with more uranium, a mixed oxide fuel, MOX, and put it in the reactor. But of course, when you mix something with uranium, you put that uranium back in the reactor and it begins to make plutonium. So the MOX solution leaves you about where you started when you finally pull out the MOX fuel. There are more clever approaches, an inert matrix fuel, inert in the sense that you put the plutonium in a material that has no uranium so that you can burn the plutonium down without creating plutonium. There's the other possibility of geologic disposal, just put the spent fuel in a repository. Or if you have reprocessing, pull the actinides, mainly plutonium, but also americium, neptunium, curium, and design durable solids for them for disposal, because spent fuel is not so durable in some geologic environments. It's the second option that I'll want to discuss. Before doing that, though, I want to show you what your choices are in the broadest sense for spent fuel cycles. The top is the once-through cycle. You just burn your fuel in a reactor, give it to a geologist to design a repository. Okay? The arrow indicates as much. A limited recycle would be to chemically process the used fuel, pull the plutonium out, put it into a mixed oxide fuel, back into a light water reactor, and then dispose of the MOX fuel. But as I've told you, you still have the plutonium in your fuel. The full recycle, the dream of my nuclear engineering colleagues, has several recycles. You do the recycle, it's called a Eurex process, to make advanced fuels. Now it's no longer MOX. By advanced, they mean inert matrix fuels and other possibilities. You put those into a light water reactor. When you pull that fuel out, you have even a more advanced processing technology where you pull the actinides out, particularly the transuranium elements, make a new fuel, and they call it an advanced reactor. By advanced, it's not really advanced. It's just one that uses fast neutrons because remember, I mentioned very briefly, you use slow neutrons to fission uranium-235, but you can, if you have fast neutrons, you can fission uranium-238. And from an energy point of view, this is exciting because we have 100 times the amount of uranium-238, and that extends the resource. What I want to point out to you is there's a geologic connection to this figure. That is, the geosciences set some of the boundary conditions for your selection between these possibilities. As you go from top to bottom, you might, or you can imagine, selecting your fuel cycle based on the abundance of uranium. If you have a lot of uranium in the ground, the once-through cycle is good enough. Burn it a little bit, put it in the ground. If the uranium resources are limited, then it becomes important, if you want to use nuclear power, to recycle, reclaim the uranium-235, reclaim the plutonium-239, and look forward to using fast reactors, reactors with a fast neutron spectrum. So that's one boundary condition the geosciences or the Earth sets on your selections. Also, as you go from top to bottom, we already practice the once-through fuel cycle. The limited recycle is used in other countries, not at the moment in the United States. And the full recycle involves new reactors that we've never built. Okay? So this is many decades away. So as we go from top to bottom, it's from could do it tomorrow to we have to keep dreaming about it. Okay? And it's about 50 years away. So if you think about the carbon cycle, you have to look at how that clock is ticking and ask yourself, well, do I really want to wait 50, 70 years for the full recycle possibility? And then finally, you see that no matter what you do, you need a geologic repository. And one of the important questions is, how important is it to burn up the actinides in a reactor? What if we just put them in the ground? Wouldn't that be a safe and effective way of disposing of the actinides? Well, there are lots of issues about putting actinides into the ground. I just want to touch on a few, and then I'll get to a little bit of the solution. The actinides affect the radioactivity, radiotoxicity, heat, and then we have to worry about their geochemical mobility. And I'll go through this quickly, but I just want to show you that fuel with or materials with or without actinides really have an impact on the strategy you use for geologic disposal. First, for radiotoxicity, this is a diagram where the black horizontal line represents the activity of about 8 tons of uranium ore, and the bright red line that starts high on the vertical axis, that's the activity of the fuel that you would make from that 8 tons of natural ore. That's the activity when it comes out of the reactor. And you can see that in terms of total activity, it takes hundreds of thousands of years before you return to the level of activity you had when you started. Okay? And I don't say whether that level is safe or not. This is just a relative argument. The green line, the thinner green line, that represents the contribution of the activity from the fission products, and the dark line represents the contribution from the actinides. And I'm not supposed to move, I know, but what you should see is that it's the actinides that extend the period, the critical period that you have to work with in terms of geologic disposal. Let's see, I had a pointer that was given to me. And so if you leave the actinides in the materials you're going to dispose of, then it will be a longer-term concern. Also, in the fuel that you dispose of, you have this mixture of fission products and actinides. And this is a little fuzzy, I'm sorry, but at 1 month you have this complicated mixture. This is in terms of radiotoxicity of radionuclides. But at 10,000 years, it's really plutonium. Okay? So with time, the actinides dominate the radiotoxicity or the safety assessment of the repository. Also, in designing a repository, some people worry about the thermal pulse. And what you can see, this solid line is the thermal output from a metric ton of heavy metal of fuel. And The only important point for this discussion is it's the actinides that hold up the thermal output for the longer periods of time. Okay? And then from a geochemical point of view, the problem with the actinides, particularly plutonium, is they have so many oxidation states. Actually, plutonium has 5. 4 we expect on a standard EH-pH diagram. And just for a geochemist, when you see multiple oxidation states, that means complicated sequences of mobility and concentration. You're going to have to model that. In addition to the solution chemistry, actinides travel by attaching themselves to colloids. This is a picture of iron oxyhydroxide colloids with uranium and plutonium attached. And we studied this in Russia some years ago because we needed a place with a strong enough signal. We needed to go somewhere where someone had just dumped a lot of plutonium into the environment. And the Russians performed an outstanding experiment in this regard. And the surprise was that the plutonium didn't travel very far in solution, but it sure covered kilometers attached to colloids. And modeling colloid transport or colloid facilitated transport can be a challenge. All of these difficulties get wrapped into performance assessments or risk assessments, which determine whether your repository passes the test. This is the dose versus time. This is an example from Yucca Mountain. The red, green, and blue lines, these are actinides. And you see that over time, they're the ones that are holding up the dose rate or the exposure to an individual in the safety assessment. Now, this is unkind, but just an inset for the neptunium, which seems to be so important. This is the data set. I just want you to see that actually what's in the performance assessment is just a scatter of data over many orders of magnitude. This represents the fact we don't know much about the soluble species for actinides in solution. And when we try to model it, we're stuck in terms of coming up with reasonable models. Or another way to say it is probably neptunium isn't such a large contributor to dose. I mean, it doesn't make any sense from a geochemical point of view. But in the absence of knowing that, one has to make what's called a conservative assumption. And so you could build actually an excellent repository and find that it doesn't comply because of the complexity of the system you're analyzing or because you've made conservative estimates that are much too conservative. Well, there's maybe a way out of this difficulty, and that's what I wanted to discuss a little bit with you, is if you look at the waste disposal strategies, key to the approach is what's called the multi-barrier system. That is, you need a good repository, you need backfill, overpack, you need a good metal canister, but inside is the waste form, the material that you first put the waste into. So one approach would be to really focus on putting the actinides in something that's extremely durable so that you don't get stuck with all of this modeling, okay? And there are reasons for doing this. Most important, I think, is near-field containment. You know, the ideal repository is one in which you don't rely on 20 kilometers of transport as the barrier. You rely on the material's properties that keep the radioactivity where it was when you put it into the ground. In a longer talk, I would try to convince you that I have a better chance of modeling the corrosion of a waste form than a hydrologist does of modeling this large piece of the Earth's crust in a risk assessment. Also, you have the possibility of natural analogs. UO2, spent fuel, exists as the mineral uraninite, UO2, and on, and I'll give you examples of that. And then finally, if you do get to chemical processing, I think we will, there are possibilities for really doing some neat material science. That is, if we start with the spent fuel and we process it, we separate some uranium, some plutonium, we have actinides and transuranic waste, we could design a crystalline ceramic or even a metallic waste form that would be very durable for certain geologic repositories. In other words, we could look at the characteristics of all of these wave streams, consider the radiotoxicity, half-life, crystal chemistry, geochemistry, the type of repository, and just do some materials design. Make something that matches. Okay. Now, for actinides, let me go back, for this part of the effort, the problem with actinides is when you put them into a material, they suffer radiation damage because the actinides decay by alpha decay events. And this is my cartoon of an alpha decay event. The alpha particle, although it has a lot of energy, doesn't displace many atoms, but the recoil nucleus displaces several thousand atoms with each alpha decay event. And in our group and others, you can do MD simulations to show these effects, but I like this poem by Roald Hoffmann. He has a book of poetry entitled The Medimix State. That's what happens when you have this radiation damage. And this is just a piece of a part of the poem, but the remnant atom, which is this recoil nucleus, transmuted, recoils, freeing itself from its lattice, cannonballs awry through a crowded dance floor. That's the perfect picture of the damage that occurs. And so you disorder the atoms, several thousand. Imagine them dancing, all properly arranged, but now this cannonball knocks them around. And with high-resolution electron microscopy, we can see this disordered recoil cascade at, say, 2 to 5 nanometers across. And that's what we're interested in, because as those cascades accumulate, they might also anneal, but as they accumulate, then there are dramatic changes in the properties. The unit cell parameters expand because of the isolated defects. The density can decrease substantially by 10 or 15%. The Bragg diffraction intensity drops as the material becomes amorphous. In other words, there's a transition, a radiation-induced transition from the crystalline state to the Medimix state. And this is a function of dose. dPa is displacements per atom. That's a convenient unit for comparing materials. Well, let me stop for a moment. I've brought you up to the Medimix state and say a little bit about how it happens that I happen to be working on it. When I was a graduate student here, I had an NSF fellowship, and it really freed me to do whatever I wanted to do. So being a little bit stubborn, I thought, well, I'm going to work on something that no one else is working on. I need to find a completely dead field without any application. And there I succeeded, because I discovered this Medimix state, and there was a wonderful, this is Adolf Pabst's presidential address, long discourse on the Medimix state and everything that's known, and reading that would kill your interest. Okay? So I thought this, and no one else was doing anything, so I thought I can work quietly here for the rest of my life. No one will notice, and things will be fine. In his paper, though, he discusses thorium silicate, THSiO4. It has 2 polymorphs. Huttonite, Colin Hutton was my advisor, and a professor here, so that kind of caught my eye. And huttonite is isostructural with monazite, an important mineral for geoscientists. And then thorite, the tetragonal polymorph, is isostructural with zircon. And Hutton made the observation, well, the huttonite's always crystalline, the thorite's always partially metamic. There seems to be a structural control. I wonder how structure controls the accumulation of radiation damage. So I thought that was a pretty interesting question. Still, no one would be interested, but at least that was a fundamental question. And another graduate student and I, Mark Taylor, we refined the structures of thorite and huttonite and published it. And I think, I won't speak for Mark, but this was the only significant thing I did while I was here. I think Mark did more significant things. And this wasn't part of either of our theses. We just did it as a hobby, and then I had the structures, and he said, okay, now, you have something to think about. Well, so that's what I did. Laboring away in obscurity, we began to work on things, and so zircon was a natural phase to work on. And the the interesting approach was to study radiation damage. This is from a zone zircon, and this is a traverse, and this is in cross polar, so you see the variations in birefringence. Well, as something becomes amorphous, the birefringence decreases, right? And so the lower the birefringence, it's hard to see in this, I'm sorry, the higher the dose. So actually across this few millimeters, I had the perfect radiation damage experiment. I knew the uranium-thorium content, I knew the age of the crystal, I could calculate the dose and measure changes in properties, and what we did was, it was the first application of transmission electron microscopy to this. Microscopes are much better now, but we could see the amorphous domains, the intermediately amorphous domains, and the early damage in the material. So this was a way to examine how materials changed as we followed this, the progress from crystalline to Medimix state. The other very interesting experiment was to dope zircon with plutonium, about 10% plutonium, and see the accelerated damage process, because the plutonium, in this case 238, has a short half-life, and so the damage would accumulate quickly. And the surprise was the damage accumulation curves and the models for the damage accumulation were very similar for both. This is an experiment that takes about 4 years, and this is an experiment that takes about 500 million years. So this was, for a material scientist, kind of an interesting data set. And you could actually extract from this information on annealing. At the same time, a very famous petrologist, Ted Ringwood, he looked at the waste management field and noticed they were putting everything in glass, which they're still doing. And he said, "Are you crazy?" He said, "Why not something much more durable?" So he came up with Synrock, a polyphase assemblage of titanates. And I think it was a very good idea. This is a TEM micrograph, and one of the phases, zirconolite, was the host for the actinide elements in the waste stream. Now, zirconolite received a lot of attention. We studied the radiation damage effects, but it had a problem, and that is when we put too much plutonium in, it changed to pyrochlore. And here's a high-resolution image of zirconolite, still crystalline, with the amorphous, the lattice fringe-free regions indicate that the pyrochlore is amorphous. Well, this was interesting, and so we studied natural pyrochlores just as we studied natural zircon. We found zirconolites surrounded by pyrochlore. In this case, the pyrochlore had 30 weight% uranium and was 100 million years old, so it was completely amorphous. And by studying suites of pyrochlore, remember this is the dose and this is the age of the samples. Remember, you go crystalline, you have a transition zone, and then finally the material becomes metamic. But looking at natural samples, what we found was that for very old samples, you had to go to higher and higher doses to make things amorphous. And that's because they were recrystallizing, they were annealing. Borrowing the approach from fission track fading, we were able to estimate that the half-life of a collision cascade in pyrochlore is 100 million years, and the half-life of the same type of cascade in zircon is 700 million years. In other words, the zircons really hang on to that damage, and it accumulates without much evidence for annealing. Well, all of this work I would say would have been considered clever and certainly continued to be unnoticed. Okay? Until it crossed paths with, I would say, good developments in the nuclear weapons area. In the early 1990s, through a series of agreements, mainly the START treaties, and START 3 has recently been approved, the number of nuclear weapons decreased because they were dismantled. And this created something like 35, 40 metric tons of plutonium for the US to do something with, and about 55 metric tons of plutonium for the Russians to do something with. And this stimulated a lot of work on, well, what materials can we store this plutonium in? Of course, nuclear engineers were saying, well, are you crazy? Let's let's put it back in the reactor and extract the energy. And finally, they've, for the most part, prevailed. But what's interesting is there's actually a very long list of minerals that have been worked on thinking about them as potential nuclear waste forms. And I want to talk about just one, the pyrochlore, because there we had, I think, interesting results. The pyrochlore, this is the general formula. If you just add up the cations, you see you have 4 and the anion 7. This is just a simple fluoride structure, AX2, except you're missing an anion and you have 2 cations. Okay? But it's just AX2 except it's AB, and it's not 2, it's 7, and you've taken 1/8 of the anions out. The pyrochlores occur naturally with in-member compositions in the B side of niobium, tantalum, and titanium. The titanium will be important. This quickly became a top candidate for incorporating plutonium and other actinides. And also you could put things like gadolinium in it, because gadolinium, a particular isotope, has a very high neutron cross-section. And if you're dealing with things that you worry about criticality, then you want something to soak up the extra neutrons, okay? Also, just in passing, I'll say, the pyrochlores become important as an inert matrix fuel, mixed with other things so that you get the right thermal conductivity. And it's important because this is a structure that's very flexible. There are over 500 synthetic compositions with lots of fascinating chemical and electrical and magnetic properties. And because the structure is so flexible, you can tailor the composition. You can burn some plutonium, but for a fuel, you have to add some rare earths. You have to increase the reactivity of the fuel, and that depends on the composition. And so you need a structure that gives you the flexibility to do that. Well, here's the fluoride structure. And you can see the simple relationship to pyrochlore. The reds are the oxygen anion, so one is missing. And instead of this being the repeat distance, as it is for fluorite, now you have an A site cation and a B site cation. And then, of course, the structure, when you pluck that oxygen out, it shifts in a very interesting way. But what's important from a radiation damage point of view, remember the cascade, when we have this cannonball go through the structure and everyone is separated from their partners, they have some choices. They could try to get back to where they were. They could organize themselves and their partners so that they make the pyrochlore structure again. Or they could only get part way. They could have disordering over the A and B sites and disorder the anion vacancy so it looks ordered, but if you looked at each person, you would see they'd be, the wrong person dancing with someone else's wife, something like that might happen. This would be the fluoride structure. Or you just couldn't get back to where you were, and it would be amorphous. So this is very important in radiation damage, it turns out, that the possibilities that are in front of you once you've been hit by this recoil nucleus make a big difference in terms of the final damage state. And the damage state matters because these are leaching data on damaged gadolinium titanate. You can see that as you go from highly ordered to amorphous, the leach rate increases by an order of magnitude. Okay? So it matters whether you're in the amorphous state, the disordered defect fluoride state, or you get back to being pyrochlore. Well, this can be studied by looking at natural minerals. I touched on that a little bit. It can be studied by doping things with plutonium and curium. But if we look at the dose as a function of storage time, it's in this region that you have this radiation-induced transformation. And so this is what we want to study, and this led us to using a technique not so often used in the geosciences, that is ion beam irradiation. We used heavy ions, or inert ions. We'd accelerate them at the sample and look at the damage accumulation. Now, almost all of our experiments were done at Argonne. In a different building is your ion accelerator. Okay, these are not tabletop experiments. But all we want are the ions which come down this pathway and into an electron microscope. And so setting at the microscope, you can start with the fully crystalline material and watch it become amorphous. You can put a heating stage around your sample or a cooling stage and do this as a function of temperature. And remember, the actinide or plutonium doping experiments took years, 4 or 5 years. The natural samples, 500 million years. This is a sequence in 15 to 30 minutes. Okay? Sometimes longer if you have to go to very, very high doses. So we have also then 3 types of data, 3 very different experiments describing the damage. And taking a series of selected area diffraction patterns, you can see the transition from fully crystalline to fully amorphous. And with the gadolinium titanate, if you've retained your crystallography, if you ever had it, looking at the diffraction maxima, you'll see from here to here we're missing some spots, and this is pyrochlore, and this is the disordered defect fluoride structure. So the gadolinium titanate disorders, survives for a little while, but at higher doses it becomes amorphous. And with high-resolution electron microscopy, we can see the change from fully ordered material, partially damaged, increasingly damaged with just islands of crystallinity, and then finally it's completely amorphous. Okay? So we get a lot of information, a lot of very detailed information about the damage accumulation process. From the ion beam experiments, we get the dose as a function of temperature, where this dose is the dose for amorphization, and you can see the curves are flat for a while and then they bend upwards at higher temperatures, and that's just where the annealing dominates. At high temperatures, the damage anneals quickly. Everyone on the dance floor is so agitated they find their partner and you get back to where you wanted to start. Sorry for hammering on this analogy, or metaphor, but I enjoy it. Okay. And then you can see there were all types of experiments done using ion beam techniques, but the most important was to demonstrate that the curium-doped and plutonium-doped samples gave us the same dose for amorphization at room temperature as the ion beam experiments. Now, the most interesting result is, what if we change the composition? That is, let's substitute zirconium for titanium. This is the gadolinium titanate curve. It corresponds to these curves. And the surprise was that by adding zirconium, the curves move to the left until finally you can no longer amorphize the material. It goes to the disordered defect fluoride structure. And when I say no longer amorphize it, that's up to over 100 dPa. And for comparison, zircon becomes fully amorphous at about 0.2 dPa. So these are very radiation-resistant materials. And what's happening, and we can see it in the high-resolution electron microscopy, is you start with pyrochlore, and then you simply disorder, and it always goes, as long as it's zirconium mainly instead of the titanium, you always go back to the defect fluoride structure, and the material remains crystalline. Well, that was the B site. What about the A site cation? Well, if we synthesized all of the titanates with all the A site, all of the rare earths in the A site. And the surprise is this curve where it bends up, refer to this as the critical temperature, that covers a range of 400 to 1100 Kelvin. What this tells a material scientist is I can design some things. If I have this type of variation in the radiation response as a function of just changing a few rare earths, then tell me how much plutonium you want, tell me the temperature, and I'll design you your waste form. Okay? That's what this is saying. And so we and others did a lot of experiments. If we start with the lanthanum zirconate, which could be amorphized at 25 K, okay, and substituted cerium, then you could see the dose increase. So literally there was a decade of work with everyone imagining or creating new compositions and generating the data from the ion beam experiments. And it can be summarized in a three-dimensional diagram where you have the size of the B site cations, the size of the A site cations, and this surface is that critical temperature. That is where the curves bend upward. And what this means is, let's say for any given, let's say gadolinium titanate, so you have the radius of gadolinium, and then you substitute zirconium, that will be just a cut through this curve, and it will look something like this, right? So if we just take that binary as an example of what we might do, and I have to say now, we'll have models for damage accumulation, damage annealing, which are based on all the data from natural samples, from the ion beam experiments, and from the plutonium and curium doping experiments. It really was a fair amount of work, but the result is simple. For the gadolinium titanate, halfway in between zirconium and titanium and the gadolinium zirconate, we can estimate very accurately the amorphous fraction, how much of this material was converted to this Medimix state as a function of dose. What you see is the gadolinium zirconate just becomes crystalline defect fluoride, but never becomes amorphous. The gadolinium titanate would be fully amorphous in 1,000 years, and the gadolinium zirconium titanate would be somewhere in between. Well, what we can do is now, here's the gadolinium titanate. We could add some calcium and plutonium, or we could add zirconium, and these are the curves for amorphization as a function of temperature. So if we put gadolinium titanate into a hot repository, it will simply accumulate the damage. There's not enough of a thermal pulse to anneal it. But if we change the composition and use the gadolinium zirconate with 10 weight percent plutonium-239, you can see that through most of the history of the repository, there would be enough heat to anneal out the damage. Or, a more recent idea, use deep borehole disposal and take advantage of the geothermal gradient. So the concept here is designing the material's response, or designing a material to respond in a known way to the radiation damage as a function of repository conditions. In this case, the most important parameter is the temperature. So what I would argue, and this is an exaggeration because we only understand a little bit one phase, but in principle, we have a fundamental enough understanding that we know how to design materials for specific conditions, and so we can make intelligent choices, say between gadolinium zirconate, which doesn't amorphize, remains crystalline, and the gadolinium titanate that finally does. And there are lots of other possibilities. There are the hafnates, the stanates. I'm just touching the top of what is now a large a large amount of work. Now, that's the story on the waste form. So I also have to say, no, still the waste management community is not so interested in this. But with those advanced fuel cycles, you have things coming out of those fuel cycles that require attention. And perhaps these ceramic materials will help. Well, it doesn't matter whether finally, from a scientific point of view, people jump on the idea. I just want to touch on where this is led, which is away from nuclear waste. If we think about radiation damage as a probe, what about pressure? And so with some trepidation, we entered the mineral physics world and began to do high pressure experiments on the pyrochlores. And the inset here shows the decrease in that critical temperature as a function of increasing zirconium content. Well, pyrochlore has a high pressure polymorph. It has several, which I would describe as distorted, disordered, and defective. Okay? The transition temperature to this high pressure polymorph as we add zirconium in a very analogous way drops with increasing zirconium content. And this is because the radiation damage is controlled by the energetics of the disordering, and in the same way, the pressure of this phase transition is controlled by the energetics of the disordering. So it's not a surprise that they're related. The other thing we've begun to do is move out of, I would say, small bits of damage and use very high energy ions, maybe 50 GeV ions. We do our experiments in Germany. There are only 2 accelerators in the world, one in Russia at Dubna, the GSI accelerator in Germany. The Chinese will have the next. There's none in the United States, but we can do very high energy irradiations, and what's important is the energies are high enough to drive the ions through the diamond cell, through the diamonds, and into the sample. Okay? So we can combine high pressures with high energy deposition. In this case, this is the rig looking at zircons, and we get the damaged tracks. Remember, the gadolinium titanate amorphizes, and it makes a wonderful track, which we can do MD simulations of with a little bit of structure. The gadolinium zirconate, those tracks anneal very quickly. In fact, you get the defect, the disordered defect fluoride structure, and that's what we see in the MD simulations. And so the focus of our work now is on what everyone else tries the phrase everyone tries to use is extreme environments. Except our extreme environment is just in this track. Here we're depositing 10 to 20 electron volts per atom. Okay, this is a huge amount of energy into this small volume, and we get to model it or observe it. And when I say huge amounts of energy, this is equivalent to 10 to the 22nd watts per cubic centimeter. Okay? That's a lot. Okay? So this is, I would say my extreme environment's more extreme than anyone else's extreme environment. So anyway. And so I'll end by saying, we started with kind of a silly attitude of looking for something that had no impact. But now it's really quite exciting. I mean, here is one of these high energy tracks, and the material explodes and quenches on the surface. Here are the diamond cells. It's maybe hard to see here. The green color is from the ions implanting into the diamond on the other side and irradiation. And now I would say a lot of people are interested in this work, and others will follow, I'm sure. So thank you for your attention. I'm happy to answer any questions.
For more, please visit us at stanford.edu.